Okay, physical science time. I don't want my necklace to bang around in here, so I'm going to move that. There we go. Let's turn that on picture-in-picture. Hopefully that works. Okay, today we're talking about one of the most fundamental things of all of science, something we talk about all of the time in science. We might even say a cross-cutting concept. Something we talk about more than in just science. One of the most basic things of the entire universe. It's your boy. No. Energy. Let's write it down. So we're actually almost, I would even say, depending on how specific you want to get, you could say that every single discussion we have in this class is about energy in some way, shape, or form. Because they are. Energy is one of the most basic things in the entire universe. Because energy is a way that we describe and measure what fundamental thing that is always happening, that has been happening since the dawn of the universe and will continue to happen forever, and some people hate it. What? Energy is a way to measure and describe. No? Good. Close, though. A measure of the ability to... This was in your vocab, which I know you did. Move is a kind of this. Yep. No? That's too specific. Motion is a kind of this thing. Your lives, puberty is a kind of this thing. Since I've been here, the tree that I'm looking at right now, that oak tree right here, out here, you see it, has grown from, when I first got here, I could probably barely see it from where I'm standing. And now, to me, because of parallax, it's as tall as the flagpole. Something has grown, changed. That's what we're looking for. Energy is a way to measure and describe change. The universe, since its beginning, has been changing. How do we know? Because it's still changing. It will not be exactly the same tomorrow as it is today. And energy is the way that we talk about change. God bless you. So, you can see even already we've talked about 3 of the cross-cutting concepts we've had. I mean, we've probably talked about all of them, but we've definitely talked about stability and change. That's one of the fundamental things we talk about in science. We've talked about energy and matter. That's one of the fundamental things we always talk about in science. And we've talked about cause and effect. That's one of the fundamental things that we always talk about in science. These are cross-cutting concepts, meaning that they apply to all of, I would say, everything, not just science, but they're issued to us as they all apply to science. Energy is the ability to cause change. Can we measure energy? Yeah, heck yeah. Measured how? In what units? No, not volts. Do you know from your reading? Did you read? Have you been working on your chapter review? The goal of me assigning this like last Tuesday is so that you can work on it. But maybe, do you remember it starts with a J? Can you think of it? Maybe we talked about it a little bit last year too. Joules. Joules, measured in joules. So we measure the ability to cause change in joules. Would someone please read me the objective?
Discuss scale, proportion, and quantity in energy measurement.
Discuss, which is what we're doing now. Scale. Give me the non-fancy words for scale, proportion, and quantity. Size, yep. Discuss scale, proportion, and quantity in the context of energy. Is that what it was? In energy measurement. If I asked you to draw energy, give me some ideas of what I could draw? A thunderbolt. That's exactly what I was hoping you would say first. Do thunderbolts change things? Yeah. Like, raise your hand if you've been struck by lightning. I haven't, actually. Raise your hand if you've been struck by lightning. Raise your hand if you've fallen in love. Do it. And the reason I bring that out is because in French and probably some other Romance languages, this is the euphemism people use for falling in love, that you've been struck by lightning. And both of those things, one is kind of an emotional, maybe you could even say hormonal experience, and the other one, fire and loud noises, and both of those are change, right? And how do we measure that change? We use the energy unit joules to measure the change in things. Could we measure the energy of a thunderbolt? Probably some way. Could we? Maybe, I don't know, maybe. How much change it causes, though? What has more energy? Let's phrase it that way. Maybe we couldn't directly measure the energy of a thunderbolt, but what has more energy? This thunderbolt or your phone battery?
Thunderbolt.
Probably the thunderbolt. This is supposed to be your phone. This is an iPhone 1. This is what you got. Steve Jobs is still alive at this time. It's got all these buttons on it. Also, I just found out like the next one, iPhone 17 or whatever it is, has a camera button. It's like, you can use the camera button. The iPhone 1 had a camera button. You took it away for 20 years, and now you're bringing it back and saying it's a feature. Pretty soon, the next one they're going to say, oh, it has a headphone jack. I remember you took that away, and now it's back again. Change. The iPhone changes, and it takes energy. Think about how much energy it takes for a group of people has to like sit together and be like, do we want the screen to be this big or this big? Do we want the battery to hold this much or this much? A group of people put in a huge amount of energy to change the iPhone. Energy is change.
Do we wouldn't just add another camera?
Do we want to put 9 cameras? 6 on the front, 27 on the back. That's 33 cameras. We got to get it going. And they sit in the room and they think about that, and it takes so much energy. Think about how much energy it takes for you to do your homework, right? You know that kind of energy. There's kind of like this cultural euphemism we use where, oh, I don't have any energy, right? You all come in, you drag your freshman bottoms in here every day, and you either say or act like you have no energy. But that means you don't feel like you have the ability to cause change today. I can't make my homework change from undone to done because I don't have energy. Does your body physically have what we're talking about, scientific energy? Yeah, where do you get that from? Food. So we really talk in science about 2 main kinds of energy, potential energy and kinetic energy. Potential energy is that energy that is, well, you describe it for me. What do you think potential energy is? Energy that is...
Like the pencil can move on the line.
Yeah, so right now, the pencil, is it moving or not? No. Could we change that? Yeah, but we'd have to put in some energy. And so we'd say that energy is stored. These things up here are higher. Do you see these cool guys up here? I don't know if the camera can pick them up, but there's like a beautiful wave sculpture and a storm glass and a little pirate ship. Do you see all those? Could those fall down? Yeah. Could they do it right this second? Probably not. They would need a little bit of change. But once they moved a little bit, because of the stored energy, because of their... One example is gravitational potential energy. Gravitational potential energy, which in, I guess, professional or college level physics, we don't abbreviate. Your book abbreviates it GPE. In college physics, we abbreviate it U. But they have some amount of gravitational potential energy. Which of those things has the most gravitational potential energy? Probably the heaviest. So we know that the mass would change it, right? What else? What has more gravitational potential energy? This cloth right here, or if I move it higher up? Higher up. So the height will change it. What else do you think? So U equals, we've got 2 of them. The mass is going to depend on the mass, and the height. What else? This one's kind of tricky to think about. What else can change? Not color. Bad guess. I don't normally say bad guess, but that was a bad guess. What? I'm trying to think of a way. It may be, let me say it this way. You said mass, which is correct, but maybe you had said, what if you had said weight? Where could the object's weight be different, even if its mass is the same? On a different planet, because it would have a different what? Yeah, gravity. Look at above Streety's head there. So on Earth we have that, which you still need to have that memorized. The acceleration due to gravity, but that can change depending on what the gravity is like in the local environment. On Earth, it's always, not just G. So U is, we already said, gravitational potential energy. M is what? Mass. Measured in what SI unit? No. Mass was measured in? No, not grams, but those are too small, so kilograms. Yep. G, again, is not just meters per second, but it's 9.8 meters per second squared on Earth. And then H is what? Height. How do we measure height in the SI? No, come on. Meters. Meters. So if we multiply kilograms times meters per second squared, you remember what that one was? We talked about this in the last chapter. Kilogram times meters per second squared is what unit that we abbreviate? Kilograms times meters per second squared is what unit? We abbreviate it in the last chapter. Times meters per second squared. So it's this. Times. Do you remember what we abbreviate this as is in the SI? It was a measure of force. Yeah, it's a measure of force, so we abbreviate this. We change this whole thing into, newtons. Okay, so we get that, but then we also multiply this by meters. And that changes it. A newton times a meter equals a guess. It's already on the board. I'll give you a hint. That actually is what we call it when we're talking about torque, but we're not talking about torque. So it is a newton meter, but it's newtons times meters, which is, it's already on the board, I told you. A measure of energy? Yes, which we measure with what unit that we've already talked about in this video? Joules. Kinetic energy, on the other hand, where potential energy is stored. And in what ways can potential energy be stored? We said by gravitational potential energy. What else? Okay, so maybe a battery. What else? Which is electrical energy, BT dub. How else can potential energy be stored?
Oh, kinetic energy.
This has got some heavy stuff on, so I don't actually want to. But if I let go of this right now,
it might kill somebody.
Yeah, it would go across the room, right? Because when I stretch it, I'm storing energy in it. What kind of potential energy do you think this is? If you had read your book, you would actually know the answer, which I know you didn't.
Elastic.
Yes, good. It was a vocab word too, I think. Elastic. And what about what we talked about earlier, the food? Did you guys get breakfast tornadoes today? Breakfast tornado is the most bussin' food from the school. But what did you get for breakfast?
Cereal.
Cereal? Okay, that's Halloween. And what kind of energy does that give your body, do you think? It is potential energy. No. Okay, maybe emotionally it gives you depression energy. It gives you, how is the energy stored in that cereal? That's not true. How is the energy stored in that cereal? In its what? Because of its what? Because of what it's made out of. What do we call that scientifically? No, scientifically. Chemical potential energy. Do you know that the food you eat is made of chemicals? Yeah, it is. You can't help it. Like I had this discussion in the staff mess hall the other day. Someone said, "Oh, I won't eat chemicals." And I'm like, you can't help it. Like everything is chemicals. This book is chemicals. Butter is made of chemicals. I know what this person meant. They meant like harmful chemicals, like pesticides or whatever. They just said chemicals. But water is a chemical. Coffee is a chemical. Milk is a chemical. I had milk for breakfast. That's a chemical. And that chemical potential energy stored in the chemical bonds, which we'll talk about later in the year. When you eat that, your body breaks it down, and that allows you to do stuff like move, kinetic energy. Not just move your limbs, which you do that too, but also like move your guts, move your blood. It causes kinetic energy. Same way, if one of these things falls down, its potential energy, its gravitational potential energy changes as it's falling to, it changes to what kind of energy as it's falling? Kinetic, exactly. So kinetic energy is the energy of motion. And we use this formula. Kinetic energy equals, do you think, let me draw the variables in this out of you again. What do you think has more kinetic energy, a heavier object or a lighter object? Heavier, for the same speed, a heavier object does. That was someone's hypothesis in their lab. So one thing you think kinetic energy definitely depends on? What I just said. No, not mass. There you go. And then what else? For a given mass of an object, what has more kinetic energy, do you think? A faster object or a slower object? faster. So it also depends probably on velocity, yeah. But actually, it depends more on velocity. It depends on the square of velocity and only half on mass. So their equation is kinetic energy equals 1/2 times mass times the velocity squared. So K is, as we said, kinetic energy. M is mass, again measured in. Oh, come on, guys. Kilograms.
Meters.
And then V is velocity, measured in meters per second, but that gets squared. And so our unit ends up being kilogram times meter squared, because this whole thing gets squared, divided by second squared, which guess what? That's a Newton times a meter, which is a joule. So even though the equation is different, they end up both being measured in joules, because that's a measure of energy. Energy can also, cannot be created or destroyed. But it can, what? Even though energy is a measure of change, it can itself change form. In Mason's lab, tell me about the way the energy changed form. It changed from what kind of energy to what kind?
Battery.
Okay, batteries is what kind of energy? Well, how do the batteries store energy?
Power.
It's actually chemical potential energy. There's chemical energy in the battery, and as that energy is released, as what kind of energy?
Fire.
No, not yet. Batteries release what kind of energy? Electrical. So the battery, chemical energy in the battery changes to electrical energy, and within the steel wool, that electrical energy changed to fire, which we call thermal energy, is heat. You should write that down. Thermal energy is heat, which is a kind of energy. So thermal energy is actually heat energy. There's also, what other kinds of energy are there in this room? Light energy, right? The light is changing electrical energy from the circuit grid to light energy, right?
Yes.
There's also sound energy. My vocal cords are changing chemical energy from the food that I ate yesterday or last week into movement, kinetic energy, which is causing sound, right? So there's sonic energy. There's all different kinds of energy, but they are always either potential or kinetic. So energy can change. If I drop something, here's the world. If I drop the world, right? Let me draw the world up here. As the world drops, when it first starts out, what kind of energy does it have? I just drew right here. Gravitational potential energy. Right here, it's 100% gravitational potential energy. And we're going to talk about two different scenarios. In one, pretend there's no air. Pretend the air is evacuated out of this part of the room. As it falls, that is what's happening to its height. Yeah, its height is decreasing. And so therefore, did its mass change? No. Did the gravitational field change? No. So if its height lowers, what's going to happen to the potential energy? It's going to lower. But wait, boy, it said that it can't be destroyed. So what's happening to that gravitational potential energy? No, the gravitational potential energy is decreasing, but what must be increasing? Kinetic. How? What part of the kinetic energy is increasing? The mass? No. But as it falls, it's getting faster and faster. And so here it has 100% gravitational potential energy, and right before it hits the ground, it has 100% what? Kinetic energy. What do you think it is right here? 50-50. Yep. Now that's the example of the fake world where there's no air resistance. In reality, as it falls, if this were true, once it hits the ground, the elastic potential energy, it would become gravitational potential energy. So if this were true and it's going 100%, it would bounce back to the exact same height. But it doesn't. Why? Some of that energy is lost. It's not really lost. It can't be created or destroyed. But because of air resistance, some of it becomes, I'm trying to make this like bigger at the bottom. More and more of it becomes what? What does the air change this into? What kind of energy does it change it into? It's gone forever? Yeah, friction. So what kind of, it generates what? Friction generates heat, which is what kind of energy? Thermal energy. Yep, very, 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 very slightly. But that is exactly true. In fact, that's how you can feel it when you rub your hands together, right? You can feel them warm up because you're transferring. Well, what you're doing is you're transferring food energy, chemical energy, into movement of your hands, and that is generating heat through friction. So one of the things friction does, you should write this down. I don't have room, but write this down. Friction changes kinetic energy to thermal energy. Friction changes kinetic energy to thermal energy. So the energies can change the type of energy. That's part of what's going on in the universe all the time, is that energy, while not being created or destroyed, is changing form all the time. And slowly, more and more and more is changing to what kind? That's not gone, but it's kind of the graveyard of energy. All of it becomes, all of the energy eventually becomes, no. This energy was not in reality lost, but it was lost because of, because of heat, because of friction. So slowly in the entire universe, with the universe as a whole, the energy is all becoming heat. Eventually, all, not just energy, but matter. Matter and energy are interchangeable, by the way. This equation, you've probably seen this equation. Have you seen that one? You've never seen E equals mc squared before? Einstein thought of this equation because matter, mass, is convertible to energy. You can switch between matter and energy. You mean you can't just be like, boy, I'm hungry, I'm going to eat some energy. Or that doesn't really work. But the sun does this. The sun converts mass into energy all the time. It takes a little bit of mass and turns it into an enormous amount of energy. That's what the sun does. That's called nuclear fusion. And over time, all the matter in the universe becomes energy, and all that energy is eventually lost to heat. And so there's this idea of the heat death of the universe, where eventually the universe will be nothing but just a constant, very low temperature, and there's no matter and no energy, and even black holes are gone. And that's the end of the universe. If nothing else happens to destroy the universe, that's how it'll end. Bye!